Hello everyone, I'm back with a home done haircut. Looking great, you don't need to tell me. We are still doing a little bit of understanding the Fundamental Theorem of Calculus. We learned the Fundamental Theorem of Calculus last week. We investigated it from several different perspectives, and the deep takeaway of all of this was something bordering on shocking or possibly obvious. And the FTC, I mentioned in the Zoom call last Friday, really has two parts to it. And together, these two parts tell us that differentiation and integration are inverse processes. And the first fundamental theorem of calculus, the one I believe to be sort of in some sense the real fundamental theorem of calculus, says that if you have some integral from a to x of some function, and this can be interpreted as a function which starts integrating under some other function f and then stops at some certain point x. So the integral from a to x of some function represents the area sort of under this curve so far, and as x changes we move to the right and we accumulate more and more area. This is what's known as an accumulator function, or I think it should be called an integral function. And if we take the derivative of this is just review, then the answer is that this is just the function. And the reason for this is because if we want to know the derivative of the integral of some function, then what we're really asking is, what is the rate at which this function is changing? And the rate at which this function is gaining area, well, at point x, if I were to get a tiny bit more area, then if x moves to the right a tiny bit, we get to some new point, say x plus delta x. And now, when we're asking for the derivative of this integral function, what we're really asking for is, what is the change in this integral function with respect to a change in x? This is the question when we're asking for the derivative of this thing. That's what we're really asking, right? How does this function change with respect to a small change in x? And the answer is, it's just how big the function is at that moment. And that's because what we have here is a rectangle whose height is whatever the function's value is at that point, and the instantaneous change, the tiny change in x is delta x. And so this is really just saying that the amount, the change in this tiny bit of area that we get is really just equal to the area of that tiny little rectangle that you just drew. And that tiny little rectangle that you just drew has area f times delta x. And since the tiny little rectangle that you just drew has area f times delta x, then the change in the area function, the integral function, is f times delta x. And written slightly differently, the change in the area, the change in the integral function with respect to a change in x is just whatever the height of the function is at that moment. Okay, that's the deep FTC. Then there's like the other FTC. And the other FTC, also deep, says that if you have some function f and you want to integrate the rate at which that function is changing, then that's f of b minus f of a. And I think this is kind of a good way of putting it. This says, the first FTC says that the derivative of the integral of the function just is that function. This says that the integral of the rate at which a function is changing is the change. And this can be interpreted, the sort of common sense geometric proof for this, which makes it in some ways just obvious, is that if you have some function, f, not depicted, and you want to know the integral of the rate at which that function is changing, then if you know the rate at which that function is changing, say this is a graph of f prime, then what I do is draw some rectangles. And what these rectangles are all estimating is the small changes in big F. The area of this little rectangle is the rate at which f prime is changing, that's what the derivative is, times a small change in x. And so if I multiply the area of that first purple rectangle is the rate at which the big F function is changing times that tiny change. And if you multiply the rate at which something is changing by a tiny change, what you get is, by a tiny change in x, what you get is a change in f. And so what you have here is the change in the big F function. That's what the area of that little rectangle represents. It's sort of like the first change in that little function, the change that occurs during that first subinterval. But then, if you consider this second rectangle, now we have a plus 2 delta x. Now the function is changing at a different rate over that second interval, but the width of that rectangle is still delta x, and the height is the rate at which f is changing. And if you multiply the rate at which f is changing by a small change in x, what you get is a second little change in f. Call it delta f2. And if you add all those up, what you eventually get is the total change in f. And so the integral, which is just the sums of all these little things, is going to give you the change in the function from a to b. And that's what the second fundamental theorem of calculus says. Okay, that was a review, possibly unnecessary, but the AP exam, which you will take, I suppose, in May of 2021, is going to test your understanding of the fundamental theorem of calculus. And the AP exam, you will find when you start doing practice for it next year, very different from the way that I teach calculus, the way our textbook teaches calculus, and actually the kinds of questions they ask are in some sense very different from the kinds of questions I ask. They assume very little background knowledge or algebra skills or anything like that. Instead, they need to ask questions that are sort of only address the very, very particular topic under discussion, and the fundamental theorem of calculus is very important, and so the AP exam has settled upon a style of question which is going to probe your understanding of the fundamental theorem of calculus. But it's at a very theoretical level. And so these questions, which we're about to do some examples of them, are sort of theoretical, abstract, artificial, and in some ways you might find them at first kind of confusing, but after you do a couple of them, they sort of make sense. And the goal of these questions are to test your understanding at a sort of a theoretical level of the fundamental theorem of calculus. So there aren't so many questions at all like this in our textbook, and because I think I should prepare you for the AP exam a little bit, and also because I think these are just good questions in general, we are going to do some practice. And so there is a packet called AP Practice Problems on the FTC. That is my title. And it's a packet which I handed out to you when we were back at school, or you can download it. Please get it now. It's 4 problems which are taken just verbatim from old AP exams from 2005, 2010, whatever. And you will find that all 4 of these questions are sort of similar but slightly different to each other, and there's almost guaranteed to be a question like this on the AP exam. So we're going to do one of them right now, and then you're going to finish this packet for homework. And so, okay, expect something sort of abstract, and in fact that's what we find. I'd like to do one, I think the one that's most representative is this one that's on page 2. So turn to page 2, please, of this packet right now, and you will find this is just cut and paste, probably like literally with scissors, from an AP exam. From who knows how long ago. After you actually started typing this into Google, you would get the year and an answer key and stuff like that, by the way. But let's talk about it now. Okay, what's going on? Here I will read aloud from the packet, but you should get it. It says, let f be a function defined on the closed interval -5 to 5 with f of 1 equal to 3. The graph of f prime, the derivative of f, consists of 2 semicircles and 2 line segments as shown above. Okay, so the most important thing to recognize is that we are being provided with a picture. This came built into the problem, and you can sort of trust this picture, you know, infinitely much or something like that, because you're told that this graph is just circles and lines. And the most important thing to note is that this is a graph of f prime. So we are going to be reasoning about this function f, but the function f itself is not depicted. Instead, what we have access to, so to speak, is f prime, and the derivative of f. And with the tiny extra little piece of information that that f of 1 is 3. Okay, so in some ways this is almost, well, we almost could have done problems like this before talking about the fundamental theorem of calculus explicitly. Because really what's going on here is we know we have some quantity, something, f, it might be position or it might be something else, and we know that the value of f at 1 is 3. So if f is a position function, it means that at time 1 we are at position 3. But we also know f prime at every moment, or at every moment we care about, from -5 to 5. So this would be the equivalent to having velocity data. So way back 3 weeks ago, when we first talked about anti-differentiation, we talked about how, in some intuitive sense, this makes complete sense. That if I know my position at time 1 is 3, and I know the rate at which I am changing at every single moment, then if I know the rate at which I'm changing at every single moment, and I know where I am at one moment, then I can reconstruct where I am at any moment. But more generally and more abstractly, if I have some function f and I know its value at one point, and I know at every moment what rate that function is changing, then I can calculate the value of f at any point. Okay, so let's go. The very first question says, find all values x at which f has a relative maximum, justify your answer. Okay, so right away, where does f have a relative maximum? Okay, and they are now testing several things. They're testing your ability to think abstractly, because they're asking questions about a function f, which is not depicted, and in fact, which cannot be described, and you're not expected to come up with a formula for f or anything like that. But they're still going to ask you questions about it. And the other thing is that they use the J word, justify. So really, I think that the hardest problem, or the thing that makes this most difficult, is not necessarily coming up with the answers, but also being able to justify your answers. Justify is like the highest level verb that they ever use. If they say justify, it means that you have to explain in clear, coherent, complete sentences, citing the names of calculus theorems, precisely why what it is you're saying is true. Okay, so first let's have the informal conversation where we figure out what the answer is, and then let's talk about what are the acceptable ways to articulate our justification. Okay, where does f have a relative max? Well, I think what makes this problem so hard is that it's so abstract. So just don't even think about this problem for a second and just answer your own question to yourself. When, in general, does a function have a relative maximum? Or rather, more precisely, how can we use calculus to determine where a function has a relative maximum? Well, this is something we learned in the differentiation unit. A function, the first derivative test says that a function has a relative maximum if the derivative changes from positive to negative. That's like a theorem that we proved. And therefore, you should be thinking to yourself, where does f have a relative maximum? Answer, when f prime changes from positive to negative. And we have access to a graph of f prime right before us. And so the correct answer to this question just involves us looking at this graph and determining when f prime changes from positive to negative. And in fact, that happens 2 times, right? At x equals -3, f prime changes from positive to negative, and at x equals 4, f prime changes from positive to negative. So by the first derivative test, those are places where f has a relative max. Okay, so that's just what you have to write. And you can't say things like, well, you know, I don't even know what you would say. Do not like ramble on about rectangles. Don't talk about positive area and negative area. Don't talk about any of that kind of stuff. You just got to go right for the end. And the end is that it's all about the first derivative test. And so the answer is f has a relative max at x equals -3 and x equals 4 because f prime changes sign from positive to negative at x equals 3 and -3 and x equals 4. F has a relative max at x equals -3 and x equals 4 because f prime changes sign from positive. That's pretty good. I think that could be like slightly improved upon, but okay. The thing is that yeah, that's basically just good. You have to specifically mention the change in sign of f prime, and okay. The thing is, you're just given a graph of f prime, so you're supposed to just report, you know, what your own eyes tell you about, you know, what f prime is doing. So you don't need to justify that f prime is indeed changing sign. It's just sort of, you just look at it. Okay, going too slow. Let's go to part B. What does part B say? Part B says, find all values x at which the graph has a point of inflection. Justify your answer. Okay, so this is, I think, tricky because different teachers all across the country and different textbooks define point of inflection slightly differently. In fact, almost everyone defines it as a point where the concavity changes, so the function changes from concave up to concave down, but people have slightly different definitions of concave up and concave down. In our class, the definition of concave up was hands up in the air, tangent lines lie below the curve. Hands under the elephant, tangent lines lie below the curve. I think this is the most honest definition. And concave down is the tangent lines lie above the curve. But other people define it differently. And so there are these sort of three interrelated concepts which are all totally equivalent to each other. One is, let's see, one is that f is concave up. One is that f prime is increasing, and the other one is that f double prime is positive. So I draw these in sort of three little bubbles or something because, and I think we did a good job talking about this back in, when we did this a month ago or something, but these three are all equivalent to each other. So in one way or another, you have to, as any calculus student, you have to know that these three are sort of three, that these are equivalent, but these are three ways of saying the same thing. The way we did it in my class is we defined concave up as tangent lines lie below the curve, and then we proved that if f double prime is positive, then f is concave up, and vice versa. So we established this, and then of course, if the second derivative is positive, then we know that means that f prime is increasing because that's what f double prime is. It's the derivative of the derivative. So if the derivative of the derivative is positive, that means the first derivative is increasing. So all three of these are just the same thing. I mention this because some textbooks will just simply define concave up as f prime is increasing, and not talk about tangent lines lying below the curve or above the curve at all. And so you should be equally comfortable with that definition. In this case, if we want to know a point of inflection, what should we be looking for? Well, we should be looking for maybe where the tangent lines lie below the curve or above the curve to f, but we don't have a graph of f. And so it's not sort of immediately clear how to use the fact that f is concave up or concave down. And we don't exactly have a picture of f double prime either, although, you know, we could reason about f double prime from the picture. But f prime, we are just looking at a graph of. And so it's sort of somehow more direct and clear or something like that to just reason about f prime. And basically, f is concave up when f prime is increasing, and f is concave down when f prime is decreasing. Therefore, if we're looking for a point of inflection, this is so long-winded. If we're looking for a point of inflection, maybe I'll even just write this. F has a point of inflection where F prime changes from increasing to decreasing or decreasing to increasing. When the first derivative stops increasing and starts decreasing, or when the first derivative starts, whichever one I didn't mention, whichever one I didn't say, that's when there is a point of inflection. Okay, so where does that happen? Well, just like by looking at the graph, we can see. And okay, here we go. This is the phrase. If you want to be very fancy, you can say by inspection, which is just your way of telling the person that you're talking to that, yeah, what I'm about to say is because I just looked at the graph, man. Where does F prime change direction, as some say? And the answer is that happens at -4 and at 2. Oh, and at -1. By inspection, F prime changes direction. I think you can just say that, or I don't know. Changes from increasing to decreasing or decreasing to increasing at, well, at x equals -4, F prime is increasing, so, and then F prime is decreasing. So at x equals -4, x equals -1, F prime is decreasing and then increasing, and x equals 2, where F prime changes from increasing to decreasing. So F has points of inflection at those places. X equals -4, x equals -1, and x equals 2. Okay, good. If you prefer to think about the second derivative, if that makes you somehow feel better, you can. If you are looking for, if you have sort of memorized or something that the points of inflection happen when the second derivative changes sign, that is true, of course. But of course the second derivative is just the derivative of the graph we're looking at. And so because F prime is increasing, the second derivative is positive, and then F prime is decreasing, so now the second derivative is negative. So there is a change in the sign of the second derivative at x equals -4. And then there will also be a change in the sign of the second derivative at x equals -1, because the second derivative will be negative here, because F prime is decreasing. But that's sort of, in my opinion, that's sort of indirect in a kind of a way, right? They've given us a graph of F prime, and so somehow the characterization of point of inflection as place where F prime changes direction is a more honest way of sort of explaining what's going on. Okay. If you wanted to, you could, in a more long-winded way, say something like, you know, because F prime changes from increasing to decreasing at x equals -4, F double prime changes from positive to negative, and therefore there's a point of inflection. But that's sort of unnecessarily extra, I think. Okay. Oh my god, long-winded video. This is terrible. We go to part C. What does part C say? Part C says now, this is sort of more just keeping it all straight in your mind. Once again, I think this is actually, no one of these questions is quite hard, but it's very abstract. Find all intervals on which the graph of F is concave up and also has positive slope. So we want to know where F is concave up and F has positive slope. Well, what does it mean to be concave up? Again, for us it means the tangent lines lie below the curve. Another person might think of concave up as being that the second derivative is positive. That's also true. But more to the point, it's when F prime is increasing. And since we have a graph of F prime, that should be what's sort of in our minds. Where does F have positive slope? Well, that's just another way of saying F has positive slope when F prime is positive. That's just what F prime is. It's the slope of the graph of F. So when the derivative is positive, then the graph F has positive slope. Okay, so basically they might as well be asking us, hey, on what intervals is f increasing and on what intervals is f prime increasing and positive? And you can kind of just look at the graph and answer where f prime is increasing and positive here on this interval from -5 to -4 and from 1 to 2. And that's kind of it. Notice how they subtly change verbs from justify to explain. So explain is a sort of lower level expectation. So you still have to sort of use complete sentences, but now it's like, you know, you can just kind of like show that you know what you're talking about. It doesn't have to be airtight. And so the answer is, the one way to answer this is, yo, it's -5, -4, and 1, 2, because, once again, you don't have to write this, but if it makes you feel better, by inspection, which is just another way of saying, dude, I'm looking at the graph, on these intervals, and if you also want to be fancy, you can write only, f prime is increasing and positive. The only indicates that not only is it the case that f prime is increasing and positive on these intervals, but that these are the only intervals on which f prime is increasing and positive. So these are the only intervals on which f is concave up and has positive slope. Okay, that would be fine. It's also, if it helps you, you could potentially, if it helps you, make a sign chart for f prime. In fact, we could have done this even earlier. And a sign chart for f double prime. So what is the sign chart for f prime? Well, it changes sign at -3, at 1, and at 4, and that's it. So just looking at f prime, we see that it's positive until -3, it's negative between -3 and 1, it's positive between 1 and 4, and it's negative between 4 and 5. F double prime, this requires some analysis. This is going to be the derivative of f prime. So you have to sort of like mentally take the derivative of this picture. Well, since f prime is increasing, the derivative will, well, let's see. Hold on, let me just put in my points first, 2, and that's it. Okay, so yeah, so now f double prime will be positive between -5 and -4 because f prime is increasing, and between -4 and -1 f prime is decreasing, and so f double prime is negative. Then f prime is increasing from -1 to 2, so f prime is increasing, so f double prime will be positive, and then from 2 to 5 f double prime is negative because f prime is decreasing. So if this helps you at all, so be it, because what were we looking for? Places where f prime is positive and f double prime is positive, is essentially, and so the answer is this and this. The reason why I don't think the number line is so helpful here is that the number line itself does not serve as an explanation. So the number line can help you think, but they still want you to explain in words always what's really going on. So you sort of still have to write this sentence. Okay. Oh my gosh. Part D. Part D asks, this is a very typical kind of question. The question is, oh man. Find the absolute minimum value of f over the closed interval -5, 5, explain your reasoning. Alright, so we want the absolute min of f on the interval -5, 5. Okay, the most important thing to recognize is that we have an entire theory on how to find the absolute minimum of a function on an interval. And the answer is, you check the endpoints, and you check all relative minima. Okay, so that's maybe just worth even writing down, right? The absolute minimum must occur at the endpoints, or at a relative minima. Okay, so this is a big thing that we did, a month ago. Anytime someone wants you to find the minimum of a function, you need to check the endpoints, then you need to find the relative minima, and then you compare the values. Okay, where does f have a relative minimum? A function has a relative minimum when its derivative changes from negative to positive. So since this is a graph of f prime, we need to find where f prime changes from negative to positive. And the answer is that only happens once, at 1. Okay, and so now we say f prime has a relative minimum at x equals 1 only because, f has a relative minimum at x equals 1 only because f prime changes sign from negative to positive. Thus, I have now explained quite clearly that this function has a relative minimum at x equals 1. And so now it suffices to do the following. I just need to compute f of negative 5, I need to compute f of 5, and I need to compute f of 1. And then, having computed these 3 y values, the absolute minimum of this function on this interval must be one of these 3. Because, never mind the fact that this is a very abstract question, the absolute minimum has to occur at a relative minimum or at the endpoints. Okay, well, one of these is really easy, and now we use for the sort of very first time that f of 1 is 3. Note that this fact was given to us at the very beginning of a problem and we never used it. So f of 1 is 3. Okay, well, excellent. That means I'm 1 down, 2 to go. What is f of 5? Well, now you are supposed to just understand the fundamental theorem of calculus so well, or it might not even be the fundamental theorem of calculus, depending on your perspective. But if I want to know f of 5, and I know that f of 1 is 3, and I know the rate at which f is changing, then this is the sort of reasoning which needs to become second nature to you. F of 5 is just f of 1 plus the change in f from 1 to 5. And the change in f from 1 to 5 is just the integral of the rate at which f is changing. I want to finish this in 1 minute. Okay, I'm so sad. I'm going to just do this really fast. What is the integral from 1 to 5 of this function? You just look at this little thing, and I guess you get like 2 or something? No, 4, wait, what? Oh, f of 1 is 3, and the integral from 1 to 5 is, what is this? That's like a 3 by 2, so that's 6, so it's half of that. So it's 3, but then minus a half, so it's 2.5. So this is 2.5, and so the answer is that f of 5 is 5.5. Okay, and then the final question is, what's f of negative